Okay, and we are off, I believe. So, let me just check if it's actually recording. Yep, okay. Okay, so I think we are off here. So, how's everybody doing? Good. Excellent. So this is going to be like super informal. I know we're in kind of like classroom configuration, but like it should be very collaborative and very, back and forth. So I figured I would give just a little bit of lecture-y stuff, kind of talk style, but definitely feel free to jump in and ask questions and such. And then I was going to go relatively quickly through the talking parts, and then we can all play around with Python a little bit. So did everybody get their PsychoPy setups running, you think, maybe? All right, cool. So we'll jump into that after a few minutes, but I'll give you a few minutes of background, and then we'll get to that. Okay, so we can probably kind of go through this. Is like adapted from a course I previously taught. You guys probably know why you want to learn to program already. If you don't, if you need a further sales job, I think this is really one of the most important general skills you can have, especially as a researcher. People keep talking about how this is going to be a thing that becomes like a basic subject in school one of these days. I just saw some link that like at Yale and Harvard, the Intro CS course is like the most subscribed course on campus, and I imagine that's true in a lot of other places too. There's all these projects like Code Academy and Code Year and IQ University and such where you can do online education and so on. And I think it's really, like, there are better resources than there ever were before. So, I think it's a good thing to do. Obviously, if you decide to jump ship from research and make actual money, coding is one really great skill that can get you some good jobs. You can save a lot of time in computing tasks. I've already told this anecdote to someone as recently as yesterday, I think, but even everyday stuff, like once you learn to program, you will often find yourself, I think, turning to programming for those things. So like, I was telling the story of a lab mate of mine who had to like counterbalance stimuli so that like her word lists were not significantly different from each other for this, this particular experiment, so that, she had like 3 lists for 3 conditions or whatever, and they all had to be balanced with regard to like word frequency and word length and all this other stuff. And it was taking her like weeks of just like shuffling words around in Excel and t-testing them all and trying to see like what was not significantly different from each other. And I looked at that, I was like, oh, well, you can just script that up and like randomize it a bunch of times and like, do this for you. And it took like an hour to code up, and then, maybe another 15 minutes of running, and it had, all the lists perfectly balanced. And she was like, I've been spending, 2 weeks doing this. So your life gets a lot easier in some ways if you invest the time up front to learn to do this stuff. Obviously, it's one of the most attractive factors that any person can have, sex or same-sex, depending on your predilection. And of course, there's like a lot of cases in psychology and cognitive neuroscience and other kinds of research where it has specific uses. So, sorry, I missed the big take-home point. And also, it's a new way of thinking. So, I think the more you kind of integrate this programming ethos into your brain, you'll find yourself thinking about things in a different way, hopefully, in a more logical, procedural way. It really, I think, helps shape your thinking, and in all kinds of ways that's helpful for like tasks, study designs, and so on. But specifically in what we do, there's lots of things that programming can help you with. You can get by using the E-prime, GUI, and so on, but if you want to get really precise timing, that your stimuli are always millisecond precise, even if you're doing some kind of rapid presentation. Doing things like generating the stimuli on the fly, so maybe you want to do some crazy thing where you are doing a visual study and you want to phase scramble all your stimuli, but you want to phase scramble them differently every 30 milliseconds or something. You can do that if you can program it. It'd be very hard to do it without programming. It's a lot easier to do adaptive, like stair-step paradigms, complex stimuli like those dot coherent studies where 20% of the dots are going in the same direction and the rest are going in random directions. You pretty much have to write code to do that kind of thing. As some of you probably are well aware, it can be tricky to send and receive codes that sync up things like timing between things like eye trackers, e.g. fMRI, or possibly all 3 at the same time, and programming will definitely help you with that. and things like real-time feedback. So, if you want to process your eye tracking signal in real time and tell participants at the end of each trial, all right, you fixated, 90% of the time. Maybe that might be built into the iLink software. I haven't used iLink, but it's not built into most of the other eye tracker software. So, if you want to do kind of real-time analyses like that so that people can get immediate feedback, programming really helps. And if you're interested on the data analysis side, things that I have done before include like getting really precise response time data from digital audio recordings with a MATLAB script. Pretty much any kind of EEG and fMRI analyses, you can click through a GUI to get that stuff done, but at some point you're going to want to do something a little more sophisticated, and then you're going to have to drop into the code or talk to someone who wants to drop into the code. Even just simple things like outlier removal. If you want to do crazy stats with Monte Carlo simulations, make cooler graphs and charts than what Excel will get you, and all kinds of other stuff like the counterbalancing thing I told you. And again, once you can do this stuff, I think the tendency is to want to apply to everything, or at least that's my tendency. So lots of reasons to learn to do this. And for those of you who are grad students, which I think is the majority, now is the time to start learning, because once you get to the postdoc and faculty stages, if you're in academia, you don't typically have a ton of time for this stuff. I mean, there are some postdocs and faculty in the room, but your time gets more and more precious as time goes on. You think you're busy now, it only gets worse. Okay. So I think probably everybody knows what programming is. This is just kind of a dumb example. But what we're really trying to do here, what we're thinking in our actual writing, is to stop thinking the way that humans do, or at least translate the way that you normally think about problem solving to this more logical structured format, right? Because brains work in parallel. They don't always follow this strict logical sequence and do the exact same thing every time, but computers do. And so you have to learn to kind of think the way the computer does so that you can program it. A podcast I like to listen to, a tech podcast, calls this empathy for the machine. So you've got to really kind of get in there and think, how does this computer going to think when I write this code, right? Not how a human would see it. So my dumb example here is from Siri. You talk to Siri. The computers are getting better at natural language processing. You can ask Siri where to hide a body, and she might tell you those kinds of things. But realistically, she's not really. Siri's not actually that smart, right? She has a few set things that she can do, but you can't just tell Siri yet. Hey Siri, do correlations between all the major brain areas activated in this fMRI study, and give the results back. She doesn't know what to do with that, right? So you still have to get your hands dirty with some code for now. And of course, the way that the computers get smarter and these tasks get easier is if we program them. And ideally, you have to use a programming language that is kind of intermediate between human language and the computer's native language. So this is a bigger point here, but just to roughly go over it very quickly, there's lots of different ways to program a computer, right? So what you're actually ultimately feeding into the computer's processor is what they call machine code, which is just numbers that the processor interprets as instructions to take these two things and add them together, or divide them, or take this thing from this location in memory and put it over here. But you could never program that because it's literally just ones and zeros. So, up from that a little bit, you have things like assembly language, which just take that machine code and put it in a slightly more human readable form. But still, you don't want to be writing code for your psychology tasks that says all right, take this byte in memory and move it over here. Now take this byte in memory and move it over here. You want a more high-level way of addressing the computer. So what people essentially do is, the very earliest programmers use these low-level languages to program and create slightly higher-level languages like Pascal, the whole C family, C, C++, C#. You may know some of these things. And then, as time goes on, people kind of say, all right, well, now we have a language that's a little bit easier for humans to use, but still can be translated into what the computer does. And we're going to use those to build even higher level languages like Visual Basic or AppleScript, something like that. Or, ultimately, possibly Siri is a way of kind of program, right? So it's just all human civilization, right? First we had fire, then we learned to shape steel, and, a couple thousand years later, we have microprocessors, right? So you kind of use the more crude tools to build yourself more and more sophisticated tools all the time. You might also think of HTML and JavaScript and things like that as programming languages. Some of them are more like programming than others, and others are just kind of describing a document. And then there's lots of other stuff, of course. But right now, we're going to focus on Python, which is a fairly high-level language, but it still has a lot in common with a lot of these languages, which, like, if you were here last time, is one of the reasons we said that Python's a good thing to learn, is because even if you don't use Python directly in your work, it will look enough like whatever you do use, and you'll be able to kind of take some lessons away from it. And ultimately, what we're hoping to do with both your brains and with all these programming languages is the idea of abstraction, right? So this is like a buzzword in computer science. It basically just means taking things further away from their implementations and making them more abstract. So, when you want to move a window around on your computer, as a human being, you don't want to think about like every single little byte of memory that has to change to like move that window across the screen, right? You want to think, all right, I've got to move a window thing. I want to move it from here to here, right? So that's a more kind of abstract level. So what we're hoping is like get more abstract over time. So we're going to start with Python, which is like a moderately abstract language. Okay, so like that's just a super quick overview of kind of like getting you into the programming space. We're just going super quick through this stuff so we can get that stuff. Okay, so I think the main kind of thing to think about for today, or to like get used to talking about for those that are just total beginners, is algorithms. I should have not put this bullet point on yet. So what is an algorithm? So what, like, you can define it lots of ways, but basically it's a fancy sounding word for like a way of accomplishing a certain task, but not just like a general sort of way, really a more specific set of instructions sense of a way of doing a task, right? So both in real life and in computing, you can accomplish lots of different tasks using lots of different algorithms, right? So whether you think about it consciously or not, you have algorithms for everything you do, right? And I think if you become, I apologize in advance, but if you become a programmer, I think you will probably find your regular life getting more and more strictly algorithmic the more time goes on. You start to obsess about like what's the most logical, best structured way to do this. There are certain things that are necessary when you're running your everyday life, right? You got to put on your socks before you put on your shoes. But then you start thinking like, all right, what's the most efficient way to like put my shoe? Where do I store my shoes so that when I'm running late in the morning, I can most efficiently get dressed in the shortest amount of time, right? Or I was thinking of this as I was putting my ice in the drink earlier. I have 2 ice cube trays in the freezer out here. And I have an algorithm for how I use ice, which is to have 2 trays full of ice, use up all the ice from the left tray, and then when that tray is empty, you take it out, move the tray on the right to the left, fill up the empty tray with water, and put it back in the right, so that you always know the one on the left has ice, and you have a buffer to swap out. And people, if you do this, I won't be that sad, but like people that just like randomly take ice from either tray and like maybe then they're both empty at the same time, those people are mad, right? Because the best way to do it is to always have like a buffer system, so that you always know you got 1 tray full of ice at any given time, as long as you don't use more than a few ice cubes at a time. So that's the kind of thing we're talking about, right? Like coming up with the best algorithm for doing something, even if something is done as organizing ice cubes, you always have ice. So that's what we mean by saying some methods are superior to others. Although that could be different. There are different criteria you're always trying to balance, right? So in life, you're always trading off like what's the fastest way to do it versus the cheapest way to do it, or most satisfying, or of course the least physical effort, or so on. In computing, that would be something like faster. Usually if you're doing some giant fMRI analysis, you want it to finish in 20 minutes instead of 3 days. But you also have to trade off things like how much memory it uses, because you can only put so much memory into your computer, or disk space, or things like that, right? So sometimes, if the fastest way would take up your entire hard disk, you might want to do it the second fastest way, and not take up your entire disk. Okay. Oh, I didn't know the survey, but it's good to have some slides for today. So another way to think about programming is it's sort of like what we do. We're writing in computer languages, and it's sort of like writing in human languages, right? I mean, the fact that we can do language as people is kind of amazing, right? Because thought is not, in its nature, perfectly linear, right? Like if you're just kind of thinking about stuff, you're activating a lot of concepts simultaneously. You are, doing a lot of operations in parallel sometimes, and you've probably had this experience many times where, like, you have an idea so clearly in your head, you feel like you have a very profound understanding of it, but then when you try to like sit down and make a sentence out of it, or a grant application or something like that, it's just, you're like, I don't understand. Like, it's so clear in here, and then like come up with the exact sequence of words in linear order that get this idea into the other person's head. That's hard, right? Because language is linear. You have to like read it left to right, top to bottom. Thought is not necessarily that way. So it's very hard to like communicate a web of ideas in kind of this linear form, right? But we're able to do it, right? We're able to put our thoughts in linear order, and that's pretty cool. And it's kind of the same thing with writing a computer program, right? Because computers can only really run their code linearly, so you have to think about the right way to structure that, just like you have to think about the right way to structure sentences and paragraphs in an essay. So there are a lot of parallels, like one of which is you'll have a better time if you outline your thoughts before you start, if you kind of like really sit down and think about what the structure of what you're doing is before you start trying to do it. And then if you're working off a good outline, even for writing code, it's relatively easy to make the code or the sentences happen if you don't have to also kind of be constantly like revising the logical structure of it because you realize you didn't think it out well enough. And so, if you're writing like paper, we would call that just like an outline. Often in writing code, we talk about using pseudocode. So I figured before we write any actual Python code, we would talk a little bit about pseudocode and like come up with some pseudocode for just an everyday life algorithm. Okay, we don't actually have to write code for this necessarily, but let's just kind of think through it. So let's say you want to make a cup of coffee. And I think for my dumb example here, just to make life even easier, we're assuming that it is instant coffee. So like you don't even have to worry about brewing the coffee, you just have like coffee mix. So this is something probably a lot of us do every day. It's easy in some sense, but if you really break it down and think about it, there are a lot of decisions you have to make before you make that cup of coffee, right? So do you want hot coffee or iced coffee, or do you want something more general that can prepare either iced coffee or hot coffee and then allow some kind of options initially to make one versus the other? What kind of brewing method do we want? I guess I kind of skipped ahead here. Do we want this to be something that varies from time to time, or just make our algorithm do one kind of coffee? What types of cups are you putting it into? What other choices do you want to allow in your coffee making algorithm? Sweetness, type of milk, etc. Do you want a half calf, triple, whipped cream, pumpkin spice latte, whatever thing at Starbucks, or do you just want like black coffee? And how do we want this to be efficient? Do we want it to be a very efficient algorithm for making one cup of coffee, or do we want it to be the most efficient algorithm for making 100 cups of coffee at one time, right? Because that might not be the same sequence of steps we use in both cases. So if we just start with the simple idea, which is 1 cup of instant coffee, and let's say we want to think about the only things we want to be kind of variable from time to time is how much sugar, how much creamer. Let's say we're just using like powdered creamer or one of those mini moo things, and how strong we want the coffee to be. And we use a standard cup size and only hot coffee for now. So what would this look like if we plan it out? So what are our steps? If these are the things we have to select. So somebody comes to you and says, all right, I want a cup of instant coffee with 2 sugar, 3 creamer, and 70% strength. How does that work? How do you do that? This is instant coffee, so what would your steps be from the instant someone tells you that that's what they want to use in cup of coffee? First thing you probably do. You have all this robot make it? Was that? You're a robot make it? Well, you're like a human robot. You're a human robot that only responds compared to what's right. Okay, yeah, so we define what they all are, but let's look. So this is a good point about abstraction. And this works for thought as well as computing. What is it? What is, right? So let's assume right now we're taking it at a moderate level of human abstraction, where we all know what the words mean. But that's a good point. You have to know kind of what level of granularity we want. All right, so you've got all these things in a cabinet. What's the first thing you might do to start making this kind of coffee? There's no real right answer. All right, so one thing you might want to do, this is jumping ahead to the finer details, but this is good. First, you might want to do an initial check to make sure you've got all your ingredients, right? You gotta check coffee, check sugar, check creamer, check that you've got cups in stock. All right, so we check all those, we've got that. What do we do next? Okay, yeah, okay, that it's very clear where people come from. Okay, so you put a kettle on, or do something to heat up the water so you don't have a hot water supply. Yep. You're clearly the one of the ones who's already done some programming, right? Yeah. So, and this is the kind of stuff we want to be thinking about, right? Because like, I think most people just say, all right, grab a cup of coffee, put some stuff in, right? But like, all these things have substance. Right? Then you got to open the cabinet. Well, open the cabinet, you got to end that. And then when you say, like, get all the stuff out in some order, right? So like cup, coffee, creamer, whatever, sugar. And then, all right, so we do that, we heat up the water, then we do what? Get a spoon, all right. Yeah, measure out the coffee, measure out the sugar, measure out the creamer. Do you use the same spoon? Probably use a different spoon. Well, it depends on whether you want coffee grounds or sugar. Yeah. This is, again, it's a little bit like being assessment compulsive, I think, to think about this stuff, right? Because you're like, all right, well, it's better if we use 3 spoons if we don't want coffee grounds and our sugar, but, you know, more efficient for the environment if we just use 1 spoon. All right, so you get the idea, right? So we have this algorithm, and we have to think about the sequencing of all these things too, right? So like, it's probably most efficient to start heating up the water first, right? Then get out all of our stuff. Then hopefully by the time we've got all our stuff out, all of our dry ingredients are like scoop out into the cup, then hopefully our water is hot enough to make coffee, and we pour the coffee in, or the water in, we have coffee, we stir it up, we're all good, right? So that's an algorithm that you might make for making a cup of coffee. So actually, let's skip ahead to a slightly more sophisticated example. I just wanted to have this last page up here. Like I said, I'll put all these slides and everything online so you don't have to write this stuff down. But there's a ton of resources that you might find helpful in your course of learning Python and programming in general. Probably a lot of you guys have already heard of many of these before, or we've mentioned them already. But just so you have them all in one place, Python.org is good for just official Python documentation. If you get the programming at all, you will find yourself on Stack Overflow constantly because you Google some weird question or error message you have. And Stack Overflow is just like a question and answer site where people like ask questions for the programmers and then other people answer, and you can upload it down to that answer. A lot of the code that runs everything you do today is copy and pasted from Stack Overflow, which is okay as long as you understand what you're copying and pasting. But if you have like more sophisticated programming issues, you will often find yourself there. I really like the book Learn Python the Hard Way. I think Josh also likes to use it, and I can not use it. And you like it, right? All right. So you can learn Python the hard way. There's also a Code Academy Python tutorial which might be helpful. Project Boiler is a fun thing if you think things like this are fun that you might want to try once you get a little bit more experience under your belt, which is basically a series of programming problems, kind of math-like problems of increasing difficulty that you can solve with any programming language. So like you want to test your skills and see if you can solve these problems. That's a good way to kind of add your skills. Yep. I'll put all the slides online, and I'm recording this session, so nobody say anything incriminating. So hopefully you'll have the voiceover too, but you'll definitely have the slides. Even if the screen recording bites the dust, you'll have the slides. There's a nice blog I like called Computing for Psychologists. That's just fun to read sometimes, including a nice bit about why every psychology student should learn code. And if you really want more of me talking about this stuff in slightly more detail, in a slightly rougher form, first kind of questions and stuff, I thought a course like this a couple of years ago with Python and MATLAB and SciPy and Toolbox. It also, I mean, these slides are from that basically. But it has a bunch of notes and concepts and sample code and more extended discussion. So if you want to supplement and want more of me talking about stuff, you can always do that. You know how to copy that link down. I'll just send you guys this. Okay, and it's got video podcasts of all the classes. All right, so let's go back. Any questions or thoughts so far before we jump into like base code and try a little bit of it? I feel like they kind of got to this. All right, so let's fire up our PsychoPy here. It's a little awkward, I know, being over here at the keyboard, but I probably have to do it. So hopefully, when you start up PsychoPy, you should get a window that looks something
Maybe. Oh, shoot. I'm having window grabbing issues. Oh, there we go. All right. It's not. Why does it not want to recognize the other screen? Come on, buddy. Was it going over? Okay, it's like being very weird that it only like actually takes the. Oh, there it goes. All right. It's like not recognizing the click and drag, but every couple of times I try it. I think it's more. All right. I think it's the screen recording is making it freak out, especially given the high screen. All right. So I'm going to maximize that. All right. So this is just to orient you before we start writing anything. This is the CyclePy interface. And this is the coder interface, I should say. If you're on the builder interface, forget that. That's for noobs. That's and not for us. So it's got the I think it's under the view menu right now. It's under the window menu. You can see how long it's been since they've actually used the builder view that I don't even remember where it is. Where is it? Oh yeah, view, builder view, yeah. So the builder view is kind of like E prime, right? You can put this stuff over there. We're not going to touch the builder view. We can do everything we want in the builder view, not builders. So to how many people, everyone on the coder view, everybody got your CyclePy or looking around with the buddy? So to how many of you is this just a totally new interface that you've never seen this coder view before? Okay, like a fair number, half or more. All right, so just to orient you very briefly to like where everything is, or everything you need for now. Basically what you've got up here is a code editing window, which is just a text editor. So like that button right here makes a new code file, which we can save, where we can type code. When you run that code, any like text it produces gets spit out into this little output window right here. Right now all it says is welcome to CyclePy. Or if you prefer, so if you don't want to write your code in there, but if you just want to test something out in Python, you got this little shell tag. And basically what this means is Python is a programming language, but it's also a program that interprets the code of that language. So basically like in this, any code we type up here in this untitled.py document is going to be just a text file, right? And normally what you do if you were running just on the command line instead of the CyclePy is when you want to then make that code go, there's a command on the command line called Python. And so you'd say Python, untitled.py, and it reads in the code, figures out what to do with it, interprets it, is what it says, and then does the stuff in that, right? So in CyclePy, that's all kind of normally integrated into the normal operation of CyclePy. So CyclePy, you have the code that you edit up here, and then when you're ready to try running it, you can just click the run button here, and it spits out the output here. But sometimes maybe you don't want to like run your whole script, you just want to cut that a command or two in Python. That's what this shell is saying. Does that sort of make sense to you if you were running some more programming? You'll see how it works in a minute if you're confused. But everybody kind of get the gist of how these things work. So basically the output from the code that you write up top goes into this little output tab. If you just want to try out commands temporarily, you can do that in the shell. Okay. So let's actually not write real Python yet, though. Let's think about our coffee example today. So let's change our minds about that single cup of coffee. And now you're making coffee for 100 people. Okay? You're making coffee all at once for 100 people. So what's going to change about our algorithm? Or what's our algorithm going to be now for maybe 100 cups of coffee instead of just one? So for the moment, let's assume that everyone wants the same kind of coffee. They want regular strength coffee, 1 cream, 1 sugar. What is our algorithm going to be for making 100 cups of coffee? Or what are our options? What are some of the reasons? Okay, exactly. So one obvious way to do it is just do what we did for 1 cup and do 100 times, right? Now what's a downside of that way of doing it? Okay, it's probably going to take longer, right? Because part of the steps of making that cup of coffee, like take everything out, you do all the coffee making stuff, put it away. But then if you're making 100 cups of coffee, you're like, then immediately taking everything out and making another cup of coffee. Right? So that's a little less efficient. So what's a more efficient way? Okay, yeah, so now we start to have some choices. So you take everything out. So you maybe only do taking everything out and putting everything away once, but then all the sub-steps you do 100 times, right? Now, you say that do it 100, do all subsets 100 times. Do you mean do all of the, like putting the coffee in the cups 100 times, or do you mean do all the other stuff besides taking it out? Like, all right.
Like if you do it 100 gallons, like 100 cups of water.
Right. So do we like, yeah, right. So do we do it like a assembly line fashion? So do we like march down the line, putting water in all the cups, and then go back and march down the line. So this is the kind of stuff you have to think about, right? Either one would be fine. You know, in real life, if you're doing this, there may be different reasons to do different things, right? So if you have 5 people helping with this, it might make sense to do, you know, one person marching down the line for the coffee mix in all the cups first, then the next person marching down the line, you know, one step behind that person, one cup of coffee behind that person, getting sugar in every cup, you know what I mean? So then every person just has to do their thing 100 times and you're done. If it's just you, maybe it doesn't make a difference. Maybe it's easier to like take the little tray of coffee stuff, get 1 cup of coffee already, step down 1 cup, do it all again, right? So these are the kind of things you want to think about.
And of course, you know, yeah, there is that question of like, well, water is heavy. Do we have, you know, do we do all that water? Well, let's just do it one way. So let's say if we're just going to like write out in pseudocode, or just basically a set of steps, you could say something like, take out, and we'll abstract away a lot of this, you know, 100 cups, and then line them up, you know, in one long line. Let's say we'll do this like tray style. So like take out tray, you know, and then like add sugar to tray, add creamer to tray, add coffee mix to tray, something like that, right? We got a tray with all our ingredients. So I guess we want a spoon too, right? Add spoon to tray. All right. We got to heat up our water. Let's assume for now that we have like superhuman strength and we can just carry 100 cups worth of water in our hands. So actually, probably before we want to take out the tray, probably that's when we want to start heating up like this 50 gallons of water, right? So actually, probably what we want to do is heat up a giant jug of water. How exactly we do that is not so important. So then that can already be heating up while we're taking out all of this stuff. And then while that's heating up, presumably we can add all of our dry ingredients to all of our cups. So we could do something like, say, for each cup, this is going to start to look more like real Python, because this is sort of similar to how you do real Python. So for each cup, what do we want to do? Like, let's say, let's not worry about dirty spoons, so let's spoon out 1 sugar, spoon out. There's a weird bug in CyclePy that apparently they have never fixed, where it makes the lines not line up like this. Spoon out 1 creamer. Are other people having that issue too? I don't know why they never ever fix that. So you have to like write arrow for 1 every time. Spoon out 1. What have we got? Coffee mix. And by the way, I could turn these off, but these little dots are basically just space indicators. Just listen to the other spaces here. I can turn the dots off, but I haven't bothered to yet. And let's see. I guess the only other thing we would want to do maybe is explicitly say move 1 cup over, right? Because we want to like physically move our tray over to the next position. All right. So we got that. And then the last thing we want to do is, well, take water off the heat, assuming we've already checked to see that it's hot enough. We can abstract that away for now. And then what do we want to do with the water? How would we structure our water adding step? Well, what do you have to do with water? I mean, you've got to put in all the cups. So we use kind of that same kind of structure we did before, right? So we could say like for each cup. I'll put a colon in, so there's that. And you'll find out more about why that is soon. And we'll say like add water to cup. Hopefully not pour it all over yourself, even though it's a giant jug of water. And move 1 cup over. And then, don't worry about putting it in there. Okay. Does that kind of like make sense structurally?
people, I mean, maybe this is a dumb example, I don't know. But the point is, we really thought out what we're going to do here, right? So we're not doing that thing where we're running all of the kitchen URLs and we're like, oh wait, I got all the stuff for tutorial, but now I've got to heat up the water still. That's going to take 15 minutes. I could have been doing that while I was doing the rice and cups, right? And we probably realized what maybe doing something like adding sugar to an empty space because you added the sugar before you actually put the cup there. But in computer programming, sometimes you do stuff like that, right? Where you accidentally get things out of order and try to do something in order to do it. So that logically structuring things make sense to people? Is that okay? Are people ready to write some actual Python code? Okay. Is everyone feeling good? So maybe let's write just a little bit of code now. So you can just get rid of this or whatever. Doesn't matter. Let's save it for posterity. I think that's regular save. I'm just going to leave it here in documents. That's fine. Copy. All right. That's not real Python code. It's not going to do anything. All right. But let's do some real Python. So actually, before we do it up here, let's try out this shell business. Switch over your shell. For those who have never written a line of code in your life, this is your initiation ritual. You can write that. Look at that. You add some text to the screen. You made a program. Yay. This hello world is often like the traditional first program people write in various languages. So you'll see this a lot if you do a lot of programming stuff. Hello world. So yeah, that's a program in a sense, or at least it's a command. So we need to see the distinction between the coder view, like top portion, and the shell thing. You can like switch over to the output, and let's do the same thing, but in an actual code file. So we could like write a line of code, say print hello world. Oh, I committed one of the cardinal sins of programming, which is that really, if you're a serious person at all, you should use a monospaced font in your, like a font like Courier, where all of the space will be same width. So forget about this help radical business. It's going to actually make me type the name of the PsychoPie, you're killing me. Let's do Monaco. I think that's it. Good. Okay. Oh yeah, because Monaco is on the output. All right. So that can actually work. Maybe if I save it and reload it. Okay, let's call this like demo1.py or something. I used Monaco. I mean, anything that like every character is the same width is going to be fine. But oh yeah. Thank you. I didn't realize I was going to be showing you. Well, it's a long story. All right, that's much better. So all of our characters are the same width now, which makes stuff line up much nicer, which is why we use it. All right, so if you've got something like Hello World in beautiful 10-point Monaco, you can then, once this is run or once this is created and saved, you can then run it up here, and you'll see in your output that it says, all right, I'm going to run the script now. We call them little program scripts, and it says Hello World. So it's the same thing, but just you can run a whole bunch of lines of code at once, as opposed to the shell, where you're basically entering in each code and looking at each piece of code and entering its output one line at a time. Everyone on board so far? Everyone completed the world? All right. Feeling good? Oh, your shell tab? I think it's. Did you find it? I think it's like here or something like that. Oops. Yeah, there's some way to do it. I can't. Let's see. Yeah, I can't remember the exact thing, but yeah. One way to do it is hit enter a bunch of times until everything scrolls off the screen. Okay. So let's try a few other things. How late do people want to go with this? Like, just read. Good stuff. And Bob is like, yes, please. All right. We'll try to keep these for now. I can go for this. So let's just do a couple basic things to illustrate some things you can do with code and then call it a day. So one of the big things that you're going to be doing a lot is working with something called variables. right? So you may remember variables in algebra, like solving for x, right? The variables here are sort of similar to math variables, except you can make them whatever you want them to be, right? Usually when you're solving for x, you're trying to find out what x is, but now you have the power, you get to decide what x is. You're the king of the variables, or the queen of the variables. So let's try something like this. We could type, we gotta get back to the real line, because the interface is a little funky, you'll find. So let's just say something like that. So some number is 42. So what we've done here basically, this is basically our x, right? You can call it whatever you want to. You can call it, Jim. But I call it some underscore number. It does have to be a contiguous chunk of text. It can't have a space in it because spaces, separators. So if I do some underscore number equals 42, that means basically what I've done is I've created a variable named some number, or x or Jim or whatever you called it, and I've assigned that a value of 42, right? So you can think of it as like make a little box called some number with a label on it, and then you put the number 42 in that little box, right? And so what the name some number refers to now is that value that you gave it, 42. So if I want to say print some number, it prints out 42, right? Because it says, all right, I know what some number is. It's that box. So I'm going to actually not print just the words some number. I'm going to print the number that is in that box. Does that make sense to everybody? Now what's the difference between what I did with print some number and print hello world? Why did it do one thing in one case and one other thing in the other case? Yes, quotation marks. So quotation marks mean treat this literally as a piece of text, rather than interpreting it as a piece of code, right? So in this case, it prints the text. Up here, in this case, it prints the value referred to by this. All right, this may be basic stuff, but just to make sure we're on the same page here.
So in the shell, is it just sitting there? It basically just continuously running whatever you're putting in, right? So
Basically.
If no matter what every time I need to call some number, it's still say.
Yep, if you put that command again in, it'll remember that. One way you can think of it, and if you want to, you can there's some way that I forget to clear and restart your shell. I know how to do this on the command line. I don't usually set it right. One way to think of this is what you do when you click the run button is basically start a shell, run all the commands in the text file, and exit the shell, right? And the actual shell tab is what lets you kind of enter those one at a time as a human typer person, and kind of see how it goes step by step. Yeah. So you can play around. So we can do the same thing here, right? So we could say, put this in our script. So these things are independent, I should mention. So the shell is not really talking to the script, okay? These are separate worlds that you're the shell is kind of like your scratch space, your scratch piece of paper. Your, script up here is some separate thing that gets run at a separate time. So you couldn't refer to something that you defined in the shell up here because it wouldn't know what's going on inside that shell. But if we did this up here and then said print some number, and notice it'll do some nice things like autocomplete text for you if you want. And it'll do nice things like you may notice it auto highlights things like print that are special words to tell you that they're special words. If we run that, hello world 42. Yay. So that's pretty cool. So we have a number in a box. We have it printing stuff. Now we can also do something maybe we don't always want the message to be hello world. Maybe we want it to be other things sometimes. So you could do something like this. You could take out that print here and say, let's make a different variable called message, for example, and set that equal to, we call text in quotation marks a string. In this case, we're making a box called message, or a variable called message. But instead of putting a number into that box, we're putting some text into that box, right? So now inside that box named message is the text hello world. So we get basically the same output if we first did these two things and then said print message followed by print some number. So if you do that, hopefully you'll see the same thing. Hello world. Right. Everybody got everybody see how that works? So you either print the literal thing, the string hello world,
Or you could print, say print a variable that refers to that string, hello world, and get that out the same way. And we didn't explicitly do this, but you could also do something like print 42, and it would give you the number 42. So, yeah. Print can take in either the name of the variable or it can take in what we call a literal, like the actual value, whether it's the number 42 or the string hello world. It knows what to do as long as numbers can't. So I should mention, I guess, if you want to name a variable 42, you're out of luck because it really tells us a name or a number. So the names for things they can have numbers in them, but they have to start with letters. So things like message and some number are good variable names. 42 would be a bad variable name because it would be impossible to tell the difference between that and just the actual number 42. That's why we don't name our kids 42. Because that would be confusing. All right. So let's do one last little thing, and I think we can call it a day. So let's try something new here. So let's try change our message a little bit just for funsies. If you don't know this reference, you are a bad person. And let's, instead of doing this, let's say something a little fancier. I'm skipping ahead a few steps here, but we're getting up to our time. So we added a little something funky here, which is a plus character. So somehow, well, let's see what it does if we just run it and find out. Whoops, what happens is an error. All right, what did I do wrong here? What? No, I didn't. Yeah, I thought I was able to do that earlier. I mix up my languages sometimes. JavaScript lets you do this totally well. Oh. Okay, I must have totally give you a bad example. Sorry. I mixed up what Python can do and what I thought that was going to be very exciting. Well, we can do it a slightly more annoying way, which is this. This is a little bit funky, but it'll get you used to some of the funky things that Python does. All right, so let's try this. This is the way I would normally do it in non-demo mode anyway. So let's try that. Oops, let's go to our output and see what it did. Yay! All right, that's what I was trying to do. So this is a little bit funkier. Maybe this is something we can return to next time. So even if you don't exactly see what's going on with, we call it the syntax, just like language syntax, UNL syntax, the punctuate and the order things have to go and so on. So the syntax may be confusing here, but what is this basically doing when we say this message.format and we put in some number? What is the effect that that has here? And what is that weird graphic? You guys see this all? Okay. Yeah, it's probably clear on the TV.
So the message string variable that we created using the bracket thing sets aside a place for a number, and then we basically tell it to print the message, but format in a very specific way with the brackets as the number, and we already had a number, so we put in some number in the brackets.
Yeah, that's pretty. Yeah, it's basically doing a substitution, right? Now, the exact rules of this are something that we won't bother with right now, but
what if there's two of those squirrely things?
Well, I was just going to suggest, let's try.
How does it know what?
Let's try something like this. And let's say let's see what happens when we run that. Oh wait, we got to put in another thing here. Okay, and run that. Oh, that's sad. All right. Right. So you can put in two placeholders. So basically, these little brackety things are just placeholders, and they're numbered kind of by their order. So usually in programming, unless you're in MATLAB, which is programmed by insane mathematicians, usually start counting zero. You get 0 to lots of places to start counting. If you want to become a real nerd, we can talk about how. or why that 0 makes more sense to start counting from the 1. But yeah, so the 0 placeholder in that sense is that like bracket 0. The 1 placeholder in that sense is the bracket 1. And then basically what we're doing, and again, we can talk more about what's actually happening here, but when we use this dot format thing, what that's saying is basically like take these things that I put into the dot format, we can call this like a function or a method, put those into those placeholders in that order, right? So you can do things like format the string and insert things in there. So we should probably wrap up if people want to kind of move on with their lives, because this, I know the first few days you do something that's kind of brain breaking and we probably don't want to do it too long. I should just mention, because we kind of jumped ahead a little bit, you can do all kinds of stuff with variables. So you can do things like a equals 5, b equals 3, and if you want to know what a plus b is, it's 8, right? So that may make a little bit more sense than even what we're just doing with messages and all that, right? So you can put different things in different boxes. You can add those boxes together. You can get the output of those boxes. You can do things like, if you want to make this a little more ponderous, you could say C equals A plus B. So that's going to make a third box named C, put the sum of A and B into it. And then if we print it, we see that what goes in there. So maybe what we'll do is, and we can, like, anyone who wants to sit around and just discuss stuff or talk about stuff, we can, but we need to stop this one part now. The thing I'd like to note, if you've never programmed before, almost every language uses the equal sign to assign a value into like a variable or a little box with a name. That's a little bit different than the way we're used to using the equal sign in math. So it's not saying what in math you're saying, like, if x equals 5, that's kind of like a statement of fact, right? Or if you have an equation like x equals y plus 1, that's like an equation for a line, but x and y can be whatever. In programming, what we're using the equal sign to do is like command C to B, in this case, the sum of A and B, right? So that equal sign means take A plus B and evaluate that, addition, but then set C equal to that. So it's not just a declarative statement, it's an imperative statement, right? So you're saying, hey C, set yourself equal to A plus B. That's a little confusing, and we'll talk about why. We'll see more why that is, can be confusing later on when we talk about trying to test whether two things are equal. But does that kind of make sense so far? This is like a very single code dipping into the waters of Python. Is it clear? Right. So I think next week I will be out of town, but I think Josh is maybe willing to lead a section. We can talk about what that'll be, and if you want to go further with this and go on. But yeah, I think everybody feels good. You feel not too terrified by Python so far. Python does not yet have you in its grip of death. All right, so let's stop for today.